Hey, welcome back to ECE 382. Kevin back here. Moving on to Module 11. Liquid Crystal Display. So that's LCD that's connected to your robot that we've used previously in the lab, the line sensors. We provided you just an output file for that so that it was just working without pretty much a black box for you guys, so you didn't know really what was going on. Today we're going to go in and actually get the LCD working. We're going to write some code to just write out data to the LCD and then also to print out characters. But first we need to talk about synchronous communication, and that's what the LCD is going to use. So all this is serial communication. That's ones and zeros being sent over a wire incrementally, one at a time, serial. But what synchronous means is that we are working with the same clock. So we're going to synchronize somehow. For this example, synchronous clock. Oh yeah, and I'm using rainbow pen today. And it's going to be based on some kind of information flag. It's going to be set to kind of allow communication to occur. All right. So the big issue that we have here is software executes quickly. At 48 megahertz. That's about 42 nanoseconds per instruction. And then hardware, on the other hand, operates slowly. So if you think about it, if we just started sending out data, at 42 nanoseconds per instruction, or 48 megahertz, probably wouldn't be that fast that you're actually sending data. But if we're sending it out as fast as we can, the hardware can't keep up. It operates about 14 microseconds to display to get a character. And then it takes about 2 microseconds to for hardware to send 1 byte. And that's if we were doing something, where we're sending information over the UART. So if our software is processing data from something coming in, it's going to go much quicker than the data can come in. Same thing pushing out to an LCD or something like that. The software is going to process it a lot quicker than it's going to be able to pass it to the LCD to display. So there's a few things we can do. There's a couple solutions to this, and they're basically down here. Blind, busy wait, and interrupts. And we have those with both input and output, right? So stuff coming to the MSP432 and the MSP432 send stuff over synchronous communication. So this the blind, which is basically this idea of we're just going to wait a certain amount of time, and that time is going to be a worst case scenario. So if I know that my hardware takes 14 or 2 microseconds to send information over a synchronous connection, then I'm going to wait more than 2 microseconds, or 2 microseconds. You can see that this is probably not a great method, because you're just sitting there waiting, and then you're gonna get information, you're gonna wait, and then you're gonna read it. It could come faster and so you could have that wasted time. The busy wait cycle, which is one of the ways we're going to implement it, is, and I think this is the way the LCD is working the way we'll have it set up is basically we're going to sit and wait while we are getting data from some external source, and then once that data is done sending, a busy flag, or sorry, the busy flag is going to be set first, waiting for data from some external device, and once the data is ready, then that ready flag is going to get set. We're going to come down, we're going to read that data, and we're going to return, and we're going to do something with that data, and we just go back and we do that forever. Interrupt is a lot nicer. So our FIFO is first in, first out buffer, just like our is the opposite of our stack, which is last in, last out. So you can think of a FIFO. It's kind of like a line. It's going to come in, the bit's going to come in, and then it's just going to go out, and it's going to be the first one out, and the bits are just going to keep coming. Kind of like, think of it like a cars into an intersection, first in, first out. And so that FIFO is going to be a global FIFO, and what's going to happen is we're going to, while the buffer's empty, we're going to just be waiting for data, and every time a device has information to provide, an interrupt is going to occur. It's going to fill the buffer, and it's going to return from the interrupt. Now the FIFO has information in it, so our main function knows, okay, we can get some information from that, and then we process it, and we get out of there. Same kind of idea for sending data to the LCD, kind of a basic, same thing. Once we have data, and the thing here is kind of think about is the hardware is up here, and down here the hardware is down here. That's why this weight has shifted, because we're going to write the data faster than the hardware is going to be able to handle it. So that's the big difference. All right, so let's talk about busy wait a little bit. The hardware will set a flag when is complete. So over here, we can see that once the hardware is ready to process more data, it's going to set the ready flag. And here it's saying when the hardware has the data to provide, it has a ready flag. So the hardware is kind of running the show because the software's already done with processing the data so fast. The software reads the flag to determine if the device is busy or ready. And then the software has to clear that flag. Signifying that the software is done processing the data. And then this flag, the flag serves as we'll see this example of this with LCD, so that this hopefully will make a little bit more sense. For an interrupt. So the hardware knows to provide more data. So this busy wait is considered unbuffered. because the hardware and software have to wait for each other during the transmission of each piece of data. So that's that ready, busy, wait kind of idea there. Um, Whereas this interrupt version is considered buffered because we have that FIFO, the data can get filled, and then especially here, as we're pushing data out, we fill the FIFO, and then the hardware can read it as it's ready for it. And then the same way on the other side is the software can empty the buffer whenever it's ready for it. All right, so let's look at a little bit of an example here. So our input device is busy collecting data. Once it's collected the data it needs, it can provide it saying, hey, I'm ready. That's that ready flag. The software reads and processes it, which reads it and then clears the flag. So that's clearing the flag. Telling the input device to, okay, we're ready for more data. And now the software can process it while it's still waiting for data coming from the input device, and we can see then we're good to go for the next one. The output opposite, so we generate and write data. We tell the output device that we have data. The output device becomes busy. The software has to wait because this output's not ready to take any more data, so it can generate the data and then wait, and then it's going to send it out again. And so you can see the software is a lot quicker. This is called I/O bound, input-output bound, because we're waiting on the hardware. If we were waiting on the software, that would be called CPU bound, but we're not doing that in this process. And that would be something, along the lines of, say like image processing. That could potentially take longer in software than it would in the hardware to provide an image. And due to algorithms and the processing of it, that's an example that could occur. All right. So let's talk a little bit more about synchronization and specifically the Serial Peripheral Interface, SPI. So that's the protocol that the LCD is going to be using. It is a synchronous system. Synchronous, again, means same clock. And it takes two different, so there's it's a master-slave construct. So basically what this means is one person's, so the clock for that, for the synchronization to occur, we have to synchronize off of one clock, and that's typically the master clock. Oh, it is the master clock. And so that's depending on which device is the master, that's who's in charge of the clock. The master is typically the one with the more processing power. So in our example, the MSP 432 is going to be the master. So it's going to be providing the clock signal to the LCD, which is the slave. And that's the clock then is now synchronized and they can communicate. Information flows in two directions, can flow in two directions simultaneously. Master out, slave in, or master in, slave out. So for example, for the LCD, we can provide, information obviously to the LCD. The LCD in this lab, or how we use it, will not be providing information back. So we'll be maintaining the master out slave in kind of construct. But if you needed information from the device, you could do it simultaneously. Okay, so transmitting device uses one edge of clock to change its output, and the receiving device uses the other edge to accept data. So it's pretty quick. So, the rising edge, transmit, falling edge, receive. So take a look at the example, just as more of a general example. But the master writes to the UC, and then the X just means there's multiple SPI or serial interfaces, so the X just is corresponding to which of the serial devices. So for this example up here, it's number 3. So it writes to buff, and then reads from RX buff. So TX transmit, RX receive. All right, so let's look at the flags. So the UCTXIFG. So UC is referring to the device. That's the serial device. Transmit and the flag. And we can look down here, and it talks. So it's an interrupt flag for the UC interface. And then this is the transmit flag. So if that is a 1, that means transmit buffer is empty, and there's room for more data to get transmitted. So that tells the software, send more data. If there is data, SPI sends it. That's the module, the controller that's running everything. And then we can transmit and receive simultaneously. Actually, let's just use the same construct there. And we can see here our master out, slave in comes along that way. That register comes in, and then the buffer gets, and then we read it. So we're not worried about this half of it too much. What we are worried about is once this flag gets set, we can provide data. That data immediately gets sent out to the input device, and that device then, if it's the LCD, will display it. As soon as information starts getting into the buffer, this turns to 0. We know then that the output device is not ready for more information, and so this is going to send it out as fast as it can, and this is going to just wait until there's room to send it. So Nokia 5110, that's a LCD from a cell phone, a really old cell phone that I guess they made way too many of, and now different little tinker shops have taken them and created these little LCDs that we can use for robotics. Basically, the big thing here, so to note, is we have our DC. That's kind of, think of that as our up here. That's our output, our MOSI. Actually, no, sorry, that's a flag. It's going to be a 1 or a 0 for data or controls. So you can change different things with the LCD, like the brightness, different things like that. So we need to set this to a 1 or a 0, depending on if we're going to send data or if we're going to send a control value. And then our clock, master out, slave in. They use a different. You can see it up here. Well, they like to just go back and forth. I like to keep it consistent. I like to have MOSI, master out, slave in, or master in, slave out. Just kind of helps keep things clear for you guys. But that's the same as master out, slave in. It always confuses me. I don't like that they switch the order of that, but whatever. All right, so now you have a kind of concept of how the information is sent. Again, the key things here are the flags and the information that's getting sent out over this buffer. And this is not a FIFO buffer. That's just an array. So basically, we put the data in the array, and that goes out when it can. All right, lab notes. Let's talk about what we're going to be doing in the lab. So I wanted to provide a little bit of background because previously to this, we've pretty much not set up or done much with writing the helper functions, but mainly just kind of working in main and stuff like that. This one, we're going to kind of set up some of the key functions so that we can control the LCD. So the command write, so this is to write a command to LCD. Basically, we need to do a few things. First, we need to wait so we are writing the portion that's kind of going on here. So we're actually writing the controller for the SPI. So we're going to send a command to, we're going to wait for the SPI to be idle, because if it's busy sending data, it can't accept more data. And if we take a look at how to do that, we can come down to here to the stat W register, and there's this flag UC busy. UC again is that that's that component that we're going to be using. We are using the serial communication interface, the enhanced universal serial communication interface in SPI mode, and we're going to use version 8, it doesn't matter. So UC, talking universal communication, busy, that's the flag that we're going to be looking for to make sure that we can send data over that serial communication. So if we wanted to do that, the way we access that flag, so it's again, we're using the enhanced universal serial communication interface. So this command here, this is going to be C code. We're going to be grabbing we're going to be using the third of these interfaces, A3. We're going to be using the stat W register because that's what this UC busy, that's where that lives. We're going to be looking at the first 0th bit, and so we want to select that bit. And we can look here. When it's a 1, it's busy. When it's 0, it's not busy. So just like we've done with systic, we can use a while uski is equal to, you don't have to call it uski, I don't know why I keep saying that, equal to something. Then we're just going to sit there and we're just going to wait. I'm going to let you guys figure out what that something is. Give you a big hint right here. All right, second step. We are sending a command. So over this DC connection here, we need to set that to a 1. 1. So this is data is 0. Nope, lied. Data is 1. Control or command is 0. All right, so that's too easy. So that's a C. If we take a look at the top of our Nokia, and this is all in Nokia 5110.c. If we take a look at the top of that file, there's something going on, some magic occurring with this command here. It's pound define. This is just a sidebar DC, and then it has some crazy pointer stuff going on, and then an address 420999058. All right. So what is happening here is instead of, so basically what's this DC is representing the address 420999058, which just happens to be the address that's connected to pin 96. So remember when we were doing our assembly coding and we had to go look up at the pin map and we're looking up the pins for, or sorry, the address map for port 1 input, port 1 output. This is the same exact thing. So if we looked at port 9 output for port 9.6, so port 9.6 output, we would find that the address equals 0x420999058. So instead of having to do port 9.6 out, sorry, port 9 out, select the bit, and then set it equal to, whatever DC is equal to 0. There's a cool functionality in Code Composer Studio, MSP 432 addressing. I don't want to get into a whole lot of detail because it's somewhat confusing, but just know that this address points exactly to port 9.6 output. So then we don't have to do all of this other stuff, and it just gives us a really cool capability. It's friendly because we're only affecting the specific pin. We're not changing all other pins. It's easy to read, and it allows us to just store it into that memory address specifically, and we don't have to worry about anything else. So you could create one of these for every pin, and they do exist actually. You just have to find them, and it's called bit banding is this concept. And it's very useful, and we'll see it throughout the code that's provided to you. And sometimes I try to not abstract it away. The TI people, they just kind of, hey, you have this functionality, use it. But I like more of just kind of trying to get you through what's going on there. All right, sorry, sidebar's over. Send data using the transmit buffer. All right, so if we look back up here, so basically what we're waiting while this is 1. We're going to not be doing anything. Once it's not 1, okay, we can send data again. And that is going to be the transmit buffer. So again, that's going to be, because we're using the third enhanced universal serial communication interface, and that's just going to be the transmit buffer. Think of that as an output, so we're going to set that equal to something, maybe the input to this function. That would be kind of useful. And then the last thing we're going to do now is, while it's busy, we're gonna wait again. Because we don't want to go start processing or doing anything else while it's trying to transmit. All right, so that is it for the command write. And I'm giving you this information because this is your pre-lab. So while yes, this video is taking a little bit longer than I'd hoped, but the cool thing is you will be able to do your pre-lab without any, hopefully, questions. All right. Oh, and just to note, I'm getting all of this flag information from that same the MSP 432 tech manual. Here are the pages, table numbers, everything about the enhanced universal serial communication interface with SPI mode. All right, so we talked about sending commands. Now we need to send data. These are going to be our characters that we're going to send. So now we are more on, so we were working here. Now we're going to be working over here. All right, so wait for the transmitter to be empty. And now we're down here with these flags. So transmit interrupt flag is set when the transmit buffer is empty. So we want to wait while it's 0. This is bit 1. Okay, so that's our, again, I'll just provide you with the register so that we're all tracking. So the key thing to note, when we do this, what we're doing is we're affecting this, or we're either reading or looking at these registers. So that's why I'm kind of trying to keep putting right next to each other. We're looking at what bit? We're looking at the second bit for this one. And basically, while there's no data there, so while it's equal to 0, we're just going to be sitting around. Cool. And then now we need to set our DC. I'll let you guys figure that out. And then we're going to actually put our data over the transmit buffer again. So very similar to what we did. We're going to send the data using transmit buffer. Cool. All right, that's the pre-lab. That's everything for part 1 of this video. I am taking module 18, which last year we did at the end of the semester, and pushing that, bring that forward. So this is going to be a change to the syllabus. I just came to, it's weird. So this is synchronous communication. Module 18 is the UART, the universal asynchronous receive and transmit. So we just talked about synchronous. In my mind, it seems like a good time to talk about asynchronous as well while we're thinking about these things. So what we're going to do is this video, part 1 of this note taker, will be due, well, you guys just finished it, so good there. But then the pre-lab for module 11 will be due lesson 20, so next lesson. And then you're going to watch a second video of this note taker, which is going to be module 18, asynchronous communication. So you can see up here we have both modules, and then we're going to do the module 18 pre-lab will be due lesson 21, and that way we can work both synchronous and asynchronous at the same time, and you guys can kind of see the synergy there, and we can talk about those while we're still on the same subject versus 6 modules later, which is about 15 lessons later. Now let's talk about asynchronous. Seems weird to me that TI did that, but I changed it. All right, until next time, later.